What's going on, Algebra Bros? It's Mr. C here, and in this video we are going to take the data provided in the table and fit an exponential model to it, as well as utilize our model to predict how much of the radioactive material will be remaining after 40 hours. So here's the situation. A nuclear scientist has a sample of 100 milligrams of a radioactive material, which has a half-life in hours. She monitors the amount of radioactive material over a period of 30 hours and obtains the following data. And you can see that data is being collected right at the get-go and then in increments of 5 hours each. So part A wants us to use a graphing utility to find an exponential model. So we're going to go to the graphing calculator in just a second, and we'll have to enter data into the L1 and L2 columns. In this table, time will represent the independent variable. In other words, these hour values will go into L1, whereas the amount remaining will represent the dependent variable, and those will be values that we enter into the L2 column. Okay? So with that said, I'm going to go to my calculator. I'll fire it up. There we go. And we're going to press Stat and enter. And in L1 are going to go all the different hour values, so 0, 5, 10, so on and so forth. Okay, be sure you press enter on that last L1 value so your calculator stores it in the table. And now the L2 values. Okay, make sure you hit enter on the 9.8 as well, so your calculator stores that. And even though it doesn't ask us for it, I would like to see what the scatter diagram looks like. So what I'll do next is press y equals and make sure that there are no equations from previous work entered in. If so, you want to clear them out. And to turn the stat plot feature on, we're going to arrow up to plot 1 and press enter, and then come back down. And you can see plot 1 is highlighted in black, meaning that your calculator will know to take the values in the L1 and L2 columns and plot them as points in the coordinate plane. To see all those points in one fell swoop, or in the same viewing window, we're going to press zoom and scroll down to option 9 where it says zoom stat. And there are the data points. So that's our scatter diagram. And you can tell that it's following some sort of exponential decay pattern. So these points are decreasing as you go from left to right, and they're decreasing in an exponential manner. So the base of the exponential function is probably going to be less than 1. Actually, it would have to be in order for the points to flow this way. So speaking of base value and everything like that, we're going to get to the actual part of the problem that we're required to find, and that's the exponential model. Let's press Stat, arrow over to Calc, and we're going to scroll down to option 0, exponential regression, which that's short for. Press enter, and you can see in this menu that it's designating the L1 values as your x values and the L2 values as your y values. We can leave the next 2 rows blank. We'll scroll our way down to calculate and press enter. And it's requesting that we write the exponential model in the format y equals a times b to the power of x, and it's providing us the values of a and b. Okay, so the value of a, and I'm going to round this to 4 decimal places. The value of a is about 99.6712, and the value of b is about 0.9258. Let me just make sure that I have those digits correct. Yep, looking good. Okay, so the format of the equation the calculator is providing these values for is y equals a times b to the x, and I'll put b in parentheses. So using these values, y is equal to 99.6712, and in parentheses 0.9258 to the power of x. And lo and behold, we do have a base value that's less than 1. If you wanted to write this according to the exponential law, in other words, as a function a of t, the amount after time t, is equal to a sub 0 e to the kt, then you could, but you would need to designate this a as a sub 0, and the value of k, I'm going to go over to the left with this, the value of k is going to be found by doing the natural log of the value of b that the calculator gave us. Alright, so I'm going to go back to the calculator and get us a decimal approximation to that. Natural log of 0.9258. And to 4 decimal places, we're looking at negative 0.0771. So that would be our value of k. Alright, so if you wanted to write this in accordance with the exponential law formula, a of t equals 99.6712 e, and then in the power of e is going to go negative 0.0771 t. And if you look at that value of k, the value of k is less than 0, indicating exponential decay. So whether we look at the base of the original exponential function or the value of k using the exponential law formula, we have indication that things are decreasing as time goes by. So for part B, it's probably pretty straightforward. For most of us here, it says use the model to predict the amount of radioactive material remaining after 40 hours. So this is a particular value of x, and it's not in the table, so we'll have to use our model to infer the value, which is the whole point. And so what I'll do is I'll take x equals 40, and we'll plug it into the, I'll use the equation that we got from the graphing calculator. So y equals 99.6712 times 0.9258 raised to the power of 40. And they want us to round to the nearest tenth, so 1 decimal point, or 1 decimal place, or 1 spot past it, and it'll be roughly 4.6 milligrams. Interestingly, if you plugged 40 into the exponential law version of the formula, you would get the same thing. Alright, so hopefully that was an exponentially exciting video for you all. Of course, if you have any questions about anything covered in it, feel free to let me know. Otherwise, thank you for watching, and have a great day.